All right. That's loud. Hello, everybody. So thanks for attending my talk. I'm pretty happy to be here. It's actually my first time at Berlin Buzzwords. So thanks to the organization for having me. I'm also pretty excited to see that the consensus is still an interesting topic. Good to see so many people in the room. The main thing that triggered me to propose this talk, put all these thoughts on distributed consensus together. It's many discussions I have been having with people, or hearing, or blog posts that people write, presentations around when consensus needs to be implemented, when consensus needs to be part of your system, coordination systems, and stuff like that. And so, in this presentation, I won't be giving a lot of new stuff. Quite the other way around. Some of the results I'll be discussing are fairly old, but it's a way of putting together my thoughts and my angle on the problem, and hopefully that will spark some interesting future conversations about all this and help us build better systems in the future. So a bit about myself. First, I would say that my core area of expertise is distributed computing. Not only building systems, but I spent quite a lot of time looking at algorithms, reasoning, and deriving algorithms. I currently work for Confluent. I'm an infrastructure engineer, and I work in the Kafka core team. If you have been following more or less what has been going on with Kafka, there is a traditional messaging layer of Kafka, but there are the things that are popping up, like connects and streams and so on. So we have various teams working on those things. But I'm still in the traditional core Kafka team. I've also been involved with open source for some time now, in particular with ASF projects, Apache Zookeeper, Apache Bookkeeper, which are projects that I have helped to create and open source. And more recently, because of my affiliation to Confluent, I've been also contributing to Apache Kafka. And I'm not involved with ASF, is Apache Incubator, helping projects to go through the Apache process until they actually graduate and become a top-level project. And before Confluent, which is a pretty recent past, I was a researcher. Initially, I was with Yahoo Research, and later I joined Microsoft Research, and then decided to endeavor into a peer development position, which is where I am right now. But let's move on and talk about the actual content of this talk. So distributed systems. There are multiple ways one can model a distributed system or reason about distributed system. Here's one angle. A collection of processes. This process, they exchange messages in order to execute some protocol. They are executing a job, processing data, whatever you like. Right? So they have a goal, they have a set of processes they need to satisfy, the properties they need to satisfy, and they execute a protocol for that. A slightly higher level view that we often have when we have a server that is exposing a set of objects with a given API is to look at a distributed system as servers that give me these objects and calls that I make against those objects through RPCs. In that case, the network is fairly transparent to those processes. They don't see the actual messages, but they're still there. That's still what's going on underneath. And in this talk, as the title implies, I'll be focusing on one particular problem, which is distributed consensus, which at a very, very high level and very informally means agreement across a set of processes. And the reason why consensus is important is that there are many problems that we cannot solve fundamentally without it. Some of the problems I will talk about, if you don't, you need consensus somewhere if you need to solve them. It doesn't mean that you need consensus in every single distributed system you do. That's definitely not the case. But it's important to draw the line and decide when it's needed, when it's not needed. And if it's not needed, cool, just find some other way of doing it. The good news is that often when we need consensus, or in the way we have been using it, it's not in the critical path of your application. So if you have frequent operations, odds are that consensus is not going to be in the critical path of those operations, even though it might be present in your system. to the problem, distributed consensus. So I have, again, a collection of processes. You can call them nodes or servers, whatever you like. I'll be calling them processes. Each of those processes proposes an initial value. It says, I think that the decision value of consensus should be 1 or 2 or 0, whatever you like. And after running a protocol that solves consensus, I want this process to agree on a value. Right? So I want all of them, or at least the ones that haven't crashed, to pick and decide the same value. And once they do it, they cannot change their mind. It has to be done only once. And as I said, it must tolerate crashes. So we are interested in scenarios in which crashes can happen. If you know a bit about the scope, there is a whole body of work considering faults that are not crash, that are Byzantine, like processes that go out of the way, become malicious, and corrupt data, send different messages to different processes. But we will not be considering those here. We have enough on our plate to discuss. But I want to make you aware that this happens and it's out there. A bit more graphically, if I have these 3 processes, P1, P2, P3, and now my initial values are colors. Each one of those processes, they pick a color to be their initial value. What I want to happen is that after running a protocol, they eventually pick one and only one. And in this case, I picked black, just for the sake of example. Okay. But what is a protocol that I could actually use to run this? And I must warn you that for the next few slides, I'll try to give some insight of how these protocols work, because I want us to be on the same page and on how these things are supposed to work in practice. But by no means I'm trying to teach you one concrete algorithm and all the features and all the details of such an algorithm. So this is just to give you an intuition of how this works. So one way is I pick a leader. So let's say that I pick P2 to be the leader. I picked P2 because I decided black in the previous slide. And that leader is going to ask the other process if they have accepted any value. And accepting here is a step towards deciding upon a value. So enough processes need to accept the value before a decision arises. So the leader asks those processes. They just started, so they haven't accepted anything. So they tell the leader that they haven't accepted anything. The leader tells them, okay, great, so accept my value, accept black. So they will go and accept black. And they will tell one another that they have accepted black. Everyone knows that enough processes have accepted black, and they go and decide black. That's awesome. However, this is not entirely safe for the following reason. Say, because again, I want to be fault tolerant, say that I had picked a different leader previously. Right? So I had picked P3 to be the leader before P2. And P3 is still lingering there. It still thinks it's the leader. Everyone else thinks it's Scratch, but it's still there. And concurrently with P2, it issues the same message. Right, asking P1 what the value has accepted. And let's say that the communication between P2 and P3 is completely delayed. Yeah. Now, P2 is unaware of P3, so it proceeds with its protocol. It tells P1 to accept black. P1 accepts black. Why not? P2 thinks it's the leader, so P2 must be right. Now, P3, and so it accepts and responds to P2. But notice that the message from P2 to P1 saying that it has accepted hasn't arrived. And so P2 thinks that it has enough processes, it has a majority that has accepted black. So it thinks, okay, great, decided black. In the meanwhile, P3 sends an accept green to P1. And P1 has no way to say, well, why should I not accept this value? P3 thinks it's the leader, so it must be right. So let's take that value too, and accept green. Now, both processes, P1 and P3, exchange accepted messages for green, they end up deciding green, which is a violation of agreement, right? Which is something I don't want, because we got into the situation that P2 decided black and the other two decided green. To get around this problem, what we have to do is, it's not standard terminology, but I like to think of fencing here. So we use, in Paxos terms, a ballot number to do the following. When I send that what value have accepted message, I send a value with it. I send a ballot number with it. And when P1 processes that message, it promises that it's not going to process any other message with a lower ballot number. And in that case, the message from P3 would just fail. Right? So if P3 tries to tell P1 to accept green, it's going to fail because the ballot number of P3 is 2. And in that case, we proceed with the protocol with black. Eventually, it tells P1 that it has accepted black. P1 decides black, and we are all good. Okay, so that was some insight on a protocol that we can use to reach, to get consensus, initial values, pick on a value, and decide it. Now, one of the reasons why consensus is hard is that because there is this well-known impossibility result behind it. The impossibility result essentially says that if I'm in a system where things can get arbitrarily slow, messages and processes, then I can get into trouble. And let's go into a bit more detail to understand what is the underlying problem. So consensus tells us that we want all processes that are still up, that don't crash, to agree on the same value. We want the decision value to be some value proposed by a process, because we don't want to get a bogus protocol that just decides upon the same thing always, and cheating and deciding, just picking the same value always. And we want it to decide eventually, which turns out to be the core of the problem. This termination condition essentially forces process to eventually decide something, and if they don't have enough information, they will end up choosing the wrong value. So let's see the intuition behind this, and this time I'm going to use just 2 processes for this, okay? So P1 and P2, each one has an initial caller, has an initial value, and let's say that I do have a 2-process consensus protocol. Now I can have the following problem. Say that I have an execution in which P1 is up, but P2 crashes right in the beginning. It doesn't send a single message out. In that case, P1 has no choice other than pick blue, so it decides blue. If I pick the symmetric execution in which P1 crashes from the beginning, then P2 has no choice other than picking green. Now, if I pick a third execution in which the message between the two are arbitrarily slow, and they cannot distinguish, so P1 cannot distinguish this execution from the first in the previous slide, and P2 cannot distinguish between this one and 2 in the previous slide, then they will end up deciding upon different values. So if I have this arbitrarily delayed communication between the two, because the processes are slow, because the network is partitioned, then bottom line is that I cannot make the right call. So clearly, this result, even though it's important and we need to be aware of it, it doesn't prevent us from running this in practice, from having systems that use consensus and that run in production successfully. The reason why that doesn't stop us is because there is a solution for partially synchronous systems. So if our system is asynchronous at times, meaning that messages get lost, or I have some, my network goes haywire, it goes bad for some time, or my processes get overloaded, whatever, then I have ops people who come and fix things, right? And then it eventually stabilizes. Then I can make enough progress to get consensus to work. And in fact, given the previous insight I gave on a consensus protocol, if I'm able to elect a stable leader, then I'll be able to make progress with it. Another important point is that if you have played with systems like Zookeeper, etcd, or just Reft for that matter, we all say that you need to have +1 process, where F is the number of tolerated crashes. And that's also fundamental results. And the argument is very similar to the one I just gave you for the impossibility. If I have less than 2f+1, if I have fewer than 2f+1, then I can end up in that situation that I just described. And again, this assumes no Byzantine behavior. Okay, great. So that was perhaps a bit too abstract. So let's go into something a bit more practical. And what is the connection between consensus and our world? So let me talk now a bit about state machine replication and atomic broadcast. It turns out that that replication is an important application of distributed consensus, and that's through this technique we call state machine replication, where essentially we split the building such a replicated state machine into agreements, just broadcasting message requests to the replicas and executing those requests. So being a bit more specific, so if I have a server that I'm going to replicate, that server will have some logic, right, that executes the commands that clients issue against that server, and some state that I use to execute the commands. That logic and state is captured as a deterministic state machine, and so what I do is I just replicate it across the replicas that I need, and I make sure that they all execute the same sequence of commands. It has to be the same sequence, because if I miss a command, I can get a replicate in a bad state, so I don't want that. Also has to be in the same order, because if I reorder, I also can get inconsistencies, so I don't want to do that. In the end, we end up with an architecture diagram that looks like this. So we have this atomic broadcast layer that takes the commands from the clients, decides upon the commands that are going to be delivered, and the order, and that guarantees consistency across my replicas. One example that I'm personally familiar with is Zookeeper, and that would look like mapping to that previous architecture. That's what Zookeeper looks like. So that atomic broadcast would be what we call ZAB, and inside the servers, we have the logic of the commands that the clients can issue against the servers, and the state would be the data tree of Z nodes we have in Zookeeper. But fine, I started with consensus, and then I went into replication, and I said that I need atomic broadcast. Atomic broadcast has something to do with agreement, but what is the connection there? It turns out that atomic broadcast and consensus are equivalent problems. They are not the same problem, right? Often, so people use interchangeably consensus systems with systems that actually implement atomic broadcast, which is not entirely wrong, because again, they're equivalent problems, but they're equivalent from an algorithm's point of view. So if we look at consensus, the calls that I have are propose and decide, whereas in atomic broadcast, I have send and deliver. And for consensus, we say that we decide upon one single value out of the values that have been proposed, and I eventually decide. And for atomic broadcast, we are interested in delivering the same sequence of messages and in the same order. So why are they equivalent? Well, it's not that hard to see. So if I give you a consensus implementation, I can implement atomic broadcast by just instantiating that consensus box, right? And so each consensus instance is going to give me a position in the sequence of delivered messages. And to get a message delivered, I propose that message to the consensus instance, and so those decided messages at the bottom give me the sequence of messages broadcast that my replicas are going to execute if I'm implementing a replicated service. Now, if you give me an atomic broadcast implementation, then I can implement consensus by just broadcasting my value as a message, and the process deliver those messages and just pick the first. In that case, everyone is guaranteed to pick the same value, and I have consensus. Okay, that sounds good, but if I am to build a replicated system, should I, so what should I do? Should I just go and implement everything that I just discussed, implement my own atomic broadcast layer, take care of this atomic broadcast algorithm, take care of reconfiguration and so on? Maybe. It's not necessarily a bad idea. It's difficult. People have said it's difficult. I think it's difficult based on my Zookeeper experience, but it's not impossible. We can do it. And if you do it, you have to, you end up picking one of those protocols that already exist, or possibly invent your own if it's needed. But then you end up having to deal with, quorum-based replication. Typically, you use majority and such. You have to deal with your own reconfiguration of your replica set. And in the case of Zeb, if you end up picking Zeb, it would look like this. And again, I'm not going through the details of the protocol, but you would need something like this in your system to make sure that every time there is a crash or every time there is a leader crash, you go through this phase where you're restoring the operation of the system, making sure that a majority has committed state so that you can start in a safe state. So that end part, the broadcast part, is essentially what I have discussed in the beginning of the talk. So an alternative to that, which doesn't completely get rid of the complexities of implementing a replicated system, is to use a configuration master, like with the vertical paxos work by Lamport and others. And this is actually what systems like Kafka and Bookkeeper use. And so let's discuss a bit those examples. You might have been in one of the Kafka talks during Buzzwords, but let me say a few words again about Kafka so that we are on the same page. So Kafka implements a messaging layer. So Kafka is a messaging layer implemented as a distributed replicated log. It exposes abstraction of topics, where producers produce messages to those topics and consumers consume from those topics. A topic can be partitioned. And in the partition of a topic, we associate a replica set with that partition. We have a distinguished replica that we call leader. It's not a fixed replica, so it can change dynamically according to failures or suspicions and such. And the other are followers. In your Kafka cluster, each one of those rows are going to be mapped to a server. So some servers are going to be leaders for some partitions, some followers are going to be, some servers are going to be followers for other partitions. And we distribute the loads across the Kafka cluster like that. So let's say, for example, that I decide that my partition needs to have 6 replicas. And I'm picking an even number here, kind of on purpose. So in Kafka, we have this notion of ISRs. I have the leader, and I need a minimum set of requests, or a minimum set of acknowledgements that I need to receive before I declare a message successfully produced. And so we can say that, for example, the ISR initially is the host set because everyone is on the same page, synced up, and so on. But the ISR obviously can change over time. So I can start again with everyone in, and then later I can decide that the 3 bottom followers are not catching up, and so I kick them out of the ISR, and so I shrink the ISR, and later on I may decide to expand as the followers catch up. So I have this dynamics of shrinking and expanding as needed. And that dynamics of that development of ISRs use Zookeeper to store the composition of the ISR. Right? So in the beginning I had 1, 2, 3, 4, 5, 6. When the bottom 3 crashed, then I kick them out of the ISR, I update the zookeeper state to be 1, 2, 3, and later when I expanded, I added the new forwards. So I can go like that. But now, given that I can have an ISR that is as small as 3 replicas, can I have a split brain scenario here? Can I have a split brain scenario here? So the answer is you can't. Because what we do is we read the ISR and we make sure that the new ISR needs to intersect with the previous ISR. So you read from zookeeper, say, oh, I have no element from the previous ISR, so I cannot become an ISR. So those 3 bottom forwards are not going to become a parallel ISR. We are not going to have a split brain. Perhaps later they will catch up and will rejoin the ISR. But there is a tricky case here, right? I can have this other scenario that looks a lot more likely to be a split brain scenario. So everyone now was part of the previous ISR, right? 1, 2, 3, 4, 5, 6, they were all part of the previous ISR. And if they just declare themselves to be part of the ISR, they legitimately, under these constraints, they legitimately can do it, right? And we could have a split brain scenario. The trouble is, we actually do a bit more than that. You cannot simply write to zookeeper. You need to write to zookeeper using versions, right? So the versions prevent that concurrent access from producing two independent ISRs. And the use of versions in zookeeper is our implementation of compare and swap. And so, giving a bit more detail, if both of them decide that to declare themselves the new ISR, they will do with the same version, and so that will clash in zookeeper. Zookeeper accept only one, and so only one of them is going to succeed as becoming the new ISR. And so if the bottom 3 try again, they won't be able to because they won't overlap with the previous ISR, which is now 1, 2, 3. The best they can do is actually sync up and catch up and rejoin the ISR. And so to get this to work, we need not only a total order of changes, right, an agreement on the order of changes to the ISR, but in addition to that, I need this ability of preventing writes that are being produced out of stale reads. And we use the versions for that. The second example, which is about Apache Bookkeeper, is not very different, but let's just go over it quickly just to see a bit of the nuances we have with Bookkeeper compared to Kafka. So in Bookkeeper, we have this notion of ledgers. Ledgers, you can think of ledgers as log segments. We have this notion of ensemble, which is the set of servers or bookies that are serving a given ledger. We don't have a leader among the bookies. Instead, we assume a single client, a single writer, and that writer is responsible for making the changes to the bookie composition. So in the beginning, the client is going to go to zookeeper and write, my ledger, starting from 0, comprises B1, B2, and B3. Now, if later on 3 crashes and I replace it with 4, then that same client is going to go to zookeeper and write 3 now comprises B1, B2, B4. If I have a single writer, then in principle I wouldn't need to use versions because there will be no conflict, no concurrent access. However, there is one special case, which is when we need to close the ledger. So we require you to close these ledgers for safely, to guarantee that upon reads, you read a consistent state. And you can have a second writer that comes just to close the ledger. Because if the first one crashes, then you might not be able to close it. And it would be open indefinitely, and you don't want that. Now, when this second client comes to close the ledger, you can end up in trouble if you, again, don't use the versions in Zookeeper. So it is, again, all about concurrent access, doing updates over your replica set in Zookeeper. But the advantage, again, between Kafka and Bookkeeper is the fact that if I use this scheme of updating the ledgers in Zookeeper or in some coordination system and using these versions, I'm able to have a more flexible replication scheme. So now comes the connection with consensus. It turns out that compare and swap is consensus number n in Herlihy's hierarchy. If you don't know what that is, it's perfectly fine. The one sentence about this is that being consensus number n means that with that operation or with that object, with a chaos object, you can solve consensus, weight-free consensus for n processes. So essentially what this is saying is that if you want to use that compare and swap, consensus must be present somewhere in your system, in particular in that implementation of compare and swap. But clearly, as I mentioned at the beginning, consensus is not needed everywhere. It's not that we attempt and we're not going to have any system without consensus. Consensus, there are objects, or these shared objects that do not require consensus. And one key example is read-write registers. So if I have anything that has a read-write interface, that will have consensus number 1, which means that you cannot reach consensus at all with that object. And in some sense, it's great. If that's your requirement, then you don't need to worry about any implementation of consensus or coordination and such. And one clear instantiation of that is a key value store, right? Where my reads are just getting the data for a key, my writes are setting the data for a key or deleting a key. But then you can come back to me and say, well, what if I want to implement a highly available key value store and I replicate it and I use atomic broadcast to solve it, right? Am I not using a strong primitive to implement this? And so does it mean that I'm all of a sudden exposing consensus even though I have this key value store interface? It turns out that you won't. Right? The fact that you have the underlying atomic broadcast there is not going to give you stronger guarantees. All you're doing there is exposing a weaker primitive. And one way of seeing that is if you take Zookeeper and eliminate some of its operations, like create, exist, get children, eliminate the conditional stuff, essentially making it a key value store. So if I do that, why doesn't Zookeeper key value store solve consensus? Here's one way of observing this. If you are to implement consensus with Zookeeper, what you would typically do is create a Z-node. So the first client to create that Z-node will put the decision value into that Z-node. But now, with this version of Zookeeper that I'm proposing here, I don't have that big enough creating anymore. I can just get and set. And so what clients can do is they can go to Zookeeper, they check if there is any value that has been written. Right? So client 1 goes to Zookeeper and says, in this /consensus, is there any value that has been written already? Zookeeper is going to say no. And client 2 is going to do the same. Zookeeper is going to say no value has been written. And now they both are going to write, and Zookeeper is not going to stop them from writing different values. Right? So client 1 is going to write 0, client 2 is going to write 1. And when client 1 receives a confirmation that has been written, he may think, okay, so now it has been decided. Now it has been decided. But then it has a problem that I have just mentioned. And you may think, okay, so what if client 1 reads again? It's not going to help because I can get that last message at the bottom from client 2 and just push it as far out as I want. And so client 1 can keep reading, see if something is going to change, and still I'll be able to write a different value. So that gives us some intuition of why if I have such an API that is weaker, won't be able to give me this consensus, a solution to consensus. All right, so to wrap up, this is a quick diagram trying to, a quick flow trying to illustrate the concepts that we have seen here. The core concept I've talked about is distributed consensus. It's it's key for implementing, it's actually equivalent to atomic broadcast, which is key for implementing replicated state machines. And that's what you need to do if you are implementing one of those. Now, I have also talked about a different way of dealing with consensus, which is by using a configuration master. I talked about 2 examples, Kafka and Bookkeeper. In both cases, we ended up needing component swap, which is consensus number n. So you still have consensus in your system if you are doing that. However, I also made the argument that not everything needs consensus, which is great. And so if you're trying to decide whether consensus is needed at all in your system, you need to essentially go and determine if, for example, you would be satisfied with a read-writing interface. And in that case, we know from our theory that consensus won't be needed. All right, and so that's everything I had to say. I hope you have learned something. And I'm ready to take questions if you have any. Otherwise, I can also take questions offline. Thank you.
All right, thanks, Flavio. We have time for 2-3 questions. Are there questions in the audience? There's one. Maybe it's okay.
Hi. If the consensus isn't part of the critical path, what does that have for consequences on when a network partition happens and or a crash happens on the processing of the messages?
Sure. So sure, that's a good question. So the question is, consensus is not in the critical path. And so what happens to my critical path when I do need to issue a consensus operation to reconfigure my replica set, maybe? You're right in that if sometimes you may have to stall, right, to reconfigure your system, or stop briefly, right? But assuming that your system is operating normally, for example, if you have a leader-follower kind of configuration as we have in Kafka, and there is no leader change, then there is no operation going to your configuration master. You still need the replication, right? So in Kafka, for example, we're still propagating the messages from the leader to the followers, right?
Any more questions?
All right.
If not, let's thank the speaker again.
Thank you.
Thanks, Flavio.